first chapter, excuse me, the first chapter in the book is chapter R. Guess what the R stands for? Stuff you're already supposed to know. Also known as review. So in my happy bubble, today will be boring as heck because you already know this stuff. But I want to go through it anyway, just real quickly, much faster than we could do in Math 1000 if we had, a whole 2 weeks to talk about exponents. Let's hit the high points. Make sure you understand why things are what they are, because in math, if you feel like the rules are changing in every problem, you're going to get really frustrated. Imagine trying to play a game where somebody's changing the rules every 3 minutes. You just give up on that game. And a lot of people give up on math because they think the rules are changing every couple of minutes. If you think the rules are changing, you don't really understand the rules. And I would be happy to help you. I'm going to help you in class, but if you want to come see me in my office and say, I don't understand why one time we do this, but the next time we do that, I'm great at answering that kind of questions. Just come see me. I want you to understand, because I know, like I said about names, I feel like my brain is completely at capacity for what I can memorize. I can't memorize anything else. I need to understand it. If I understand it, then I don't just have a bunch of garbage memorized. I can figure it out. And that's my goal for you when we get down to these exponent rules. My Roman numerals are what the different directions in your homework say. The very first type of problem in the homework says find the domain of the variable. And the domain of a variable is just what you can let the variable be without blowing the expression up. And when I say blowing the expression up, give me an example of something that blows up a fraction. What can you not allow to happen in a fraction? 0 in the denominator of the fraction. 0 in the numerator is not a problem. If you have no cookies, 0 cookies to divide up among your 3 children, how many cookies does each child get? 0, but there is an answer to that question. 0 divided by 3 is 0. It's when you have 3 cookies to divide by 0 children that your calculator starts smoking. All right, so find the domain is find what x can be, and usually we're talking about fractions, and you have to watch out for what makes the denominator 0. Another thing you can't allow to happen, as long as you're in the realm of real numbers, you can't take the square root of a negative without getting into imaginary numbers, which we'll do a little bit later. But for right now, I'm going to say square root of a negative number would be a problem. And so that's something I would have to watch out for. That's the 2 big things we have to watch out for at this point. 0 in the denominator of a fraction, or whatever gives us a negative under the radical. I want to make sure, totally sure, that nobody in here is going to have a problem distinguishing between these 2 examples. And again, I don't want you to memorize. If 0 on top is okay, 0 on bottom is bad. If that's how you're learning math, you're going to forget it. But if you understand what division means, you can figure out which one of these is 0 and which one's undefined. Think about what division means. If I say 8 divided by 4 is 2, I know it is because I can check that. How do you check 8 divided by 4 is 2? 8 divided by 4 is 2.
4 times 2.
Yeah, the answer times the denominator has to give you the numerator. And I don't have to wait for a teacher to grade that paper. I checked it myself. I know it's right. So what about 0 divided by 4? What do you think it is? 0? And somebody's going, oh, I don't know, that might be the one that's undefined. Well, you can check it. If you put 0, then how should you be able to check that? The same way we check this. The answer times the denominator has to give you the numerator. And is that a true statement? Yeah, 0 times 4 is 0. So this answer is 0. I know that, not because somebody told me so, but because I can check it. And so if I see this problem on a test, and I go, well, that's 0 as well. Well, if that's 0, I should be able to check it. What statement would have to be true if that was the right answer? 0 times 0, the answer times the denominator, would have to give you the numerator. Is that a true statement? No, and I don't want you to walk out with that in your notes, or you'll show somebody and they'll come fire me. Put a question mark, like I was trying to figure out if that was true. A question mark here, like I was trying to figure out if that's true, and that is definitely not true. So 0 is not the answer to this problem. Actually, there is no answer to that problem, which is why we call it what? Undefined. There's no number in the whole wide world that we can multiply by 0 and get 4 as an answer. So that is an expression that does not exist. That's an expression that's undefined. All right, so in the homework, you'll have some problems that say find the domain. And if our original problem is a fraction, what's the thing we're watching out for? The thing we can't allow to happen. 0 in the denominator. What's the only value of x there that would give us 0 in the denominator? 2. So I could either say, here's the best way to write it. You could say x cannot be 2. And when you write that for the domain, I understand that you mean x can be anything other than 2. There's no number that will blow this up except for 2. So 2 is the only number you have to eliminate from the domain. With radicals, we're watching out for anything that would make us be taking the square root of a negative, because the square root of negative is not a real number. Give me an example of a number you could let x be here. There are thousands, millions, billions of them. Just give me one number that you could let x be. 3? Square root of 3 minus 2 is not a problem. That's a good one. What else could I let x be? I could let x be 4. I'd have square root of 2. That's not a problem. Give me a number that I could not let x be. 1. I heard 1. If I let x be 1, I'd have the square root of what? And that's an imaginary number. I cannot let x be 1. I heard somebody say 2. Could I let x be 2? That would give me square root of 0. And can I take the square root of 0? Yeah, that's not a problem. So you've given me examples of things I could let x be, and you've given me examples of things I could not let x be. But how do I describe all the numbers I can let x be?
Less than 2.
You're saying
It cannot be less than 2.
Greater than or equal to 2.
all right, when you say x cannot be less than 2, you said that's the same thing as x is greater than or equal to 2. And that's exactly right. For the domain, I want to write what x can be. And with an inequality symbol, I can say x can be anything greater than or equal to 2. Anything bigger than 2, if you subtract 2, you'll still get a positive. Or 2 itself, if you subtract 2, you'll get 0, and that's not a problem. Another way you could write that in interval notation, we'll talk about it more in 1.4, but does anybody remember interval notation? If I was going to graph all the numbers greater than 2, I'd put a closed dot on 2 and shade to the right. What's that symbol we use when we shade forever to the right? That's infinity. And so in interval notation, we could say x can be anything from 2 to infinity. These three things all mean the same. This is inequality notation. This is a graph, and that's interval notation. But they're all saying x can be anything 2 or bigger. And in interval notation, when we talk about it more in 1.4, you'll see a bracket means the 2's included. If the 2 was not included, I'd use a parenthesis. But you don't have to remember that right now. What about this last one? Square root of 2 minus x. Give me an example of a number you could let x be. Negative 2? Because what's 2 minus negative 2? Better known as, and that's not a problem. So I could let x be negative 2. Could I let x be 2?
Yeah.
Square root of 0 is okay. Give me an example of a number I could not let x be. I'm sorry, what?
3.
3, because that would give me square root of negative 1, and that would be a problem. So you've given me an example of what I could let x be and what I could not let x be, but how would you write that domain as an inequality?
X is less than or equal to 1, 2. Okay.
If you want to subtract a number from 2 and not get a negative, you're going to have to subtract numbers that are smaller than 2 or equal to 2. So as an inequality, the way you write anything smaller than or equal to 2 is just x is less than or equal to 2. All right. So the first thing in the homework is find the domain. Second thing in the homework is everything you ever wanted to know about fractions. Not fractions, exponents. I don't know why I said fractions, exponents. This semester we're going to try to use the right words for stuff. We're not going to say the little number up in the air. The little number up in the air is called the what? The exponent, and the number that the exponent applies to, the big number below it's called the base. Here's my first big caution for you. Where is it? Right here. Pay attention to the base. Without parentheses, the exponent only applies to what's immediately below it, not any pluses or minuses or anything else in front of that number. So you really have to pay attention on problems with exponents and say, what is the base here? What is this exponent being applied to? Of these next two examples, 10 out of 10 dentists surveyed will get that first one right. Negative 5 in parentheses squared means the base is what? Because of the parentheses, the base is negative 5. The negative is part of what's being squared. This expression means negative 5 times negative 5. And we all know that a negative times a negative is a positive. So 10 out of 10 dentists surveyed will get that one right. 9 out of 10 dentists surveyed would miss this one because of not paying attention to the base. Without parentheses, what does that exponent 2 apply to? Just the 5. Here, zoom out just a little bit. In example 1, the base was negative 5 because the negative was in parentheses, but in example 2, the base is just 5. A big part of math is training your brain to look at an expression the right way. And if there's a way that I could rewrite this second example that would help my eyes understand or see better that the negative's not part of the base, I'd write it that way. I could write this as negative 1 times 5 squared. And then it's very clear to my eyeballs that that negative is not being squared. That's negative 1 times 25. That's why that answer is negative 25. So anytime I have a negative that's not part of the base, for example, another example, negative x squared, I'm going to write it as negative 1 times x squared, just so I can see the negative is not part of the base. All of the rules in math are what they are because somebody noticed the pattern. We're working our way up to the definition of zero exponent, and we're going to discover it by using a pattern. If we start with the statement 3 to the 4th is 81, that's a true statement, right? It's an equation that says these two things are identical to each other. We know that one of the things we can legally do to an equation is divide both sides by the same number. So if we divide both sides of this equation by 3, we get a resulting equation that's also true. If we divide by 3 again, we get a resulting equation that's always also true. And if we do that one more time, we're down to 3 to the first equals 3, still a true statement. As a matter of fact, I could have written out here, that's the definition of the exponent 1. The definition of the exponent 1 is anything to the first is still itself. I didn't type that. But what do you notice? Each time I divide by 3, what's happening to these exponents on the left-hand side? They're decreasing by 1. I started with 4 and then 3, 2, 1, 0. So if I divide by 3 again, the next exponent is going to be negative 1. Well, to figure out what, you know what? Let's skip one. Right here. If I divide both sides by 3, I'm down to the exponent 0. On the right-hand side, if I divide by 3, I get to 1. That's the definition of the 0 exponent. Anything to the 0 is 1. Seems like it ought to be 0. Anything to the 0 seems like it ought to be 0. But when I kept repeating this pattern of dividing both sides by 3, I didn't end up with 0 right there. 3 divided by 3 is 1. And that's why anything to the 0 is 1. If we take that step one, or that pattern one step further, our exponent is down to negative 1. What about on the right-hand side when we divide by 3? If we divide 1 by 3 and just leave it a fraction, what will that fraction be?
1/3.
1/3. That's interesting. Here I had 3 to the negative 1. Here I had 1 over 3. I'm trying to discover a pattern here. What about 3 to the negative 2? What's 1/3 if I divide it by 3? 1/9? That's exactly right. And I just happened to notice I could write that 1/9 as 1 over 3 squared. I don't know why I would want to do that, except for it helps me see the pattern that's going on here. 3 to the negative 1 is 1 over 3 to the positive 1. 3 to the negative 2 is 1 over 3 to the positive 2. If I can squeeze one more step in there, 3 to the negative 3, that's 1 over 3 to the positive 3. In other words, taking the reciprocal of the base makes the exponent positive. I'm going to hypnotize you. You are all susceptible to hypnosis. You just didn't know it until now. From now on, when you see a to a negative exponent, whenever you see a negative exponent, there's an R word that I want to pop into your head, and it's reciprocal. So from now on, when you see a negative exponent, you're going to think reciprocal. And then you'll remember the whole sentence. Taking the reciprocal of the base makes the exponent positive. It's how we rewrite expressions that have negative exponents so that they have positive exponents. These 10 examples are just going to make sure that you're paying attention to the base and you understand zero exponent and negative exponent. And notice, I don't know why I went like this, but this 1, 2, 3, 4 goes across instead of down. So what about number 1? 5 to the 0 is what?
1.
Anything to the 0 is 1. What's the base of the exponent 0 in number 1? The base is 5. Is it the same base in number 2? The base is 5x. It's still something to the 0. What's something to the 0? 1. If I say what's 7 to the 0, it's 1. If I say what's q to the 0, it's 1. If I say what's rhinoceros to the 0, it's 1. Anything to the 0 is 1. So why isn't the answer to number 3 1?
Because 5 is in parentheses.
Because the 5 is not part of the base. Y'all said that well. Here's how I can train my eyes to see it better. It's amazing what a dot can do. But if I put 5 times x to the 0, then it's very clear to me that that 5 is not part of the base. And you don't need to write in a middle step. If you're doing all the homework and you're making hundreds on it, then whatever you're doing is okay. I'm just writing down middle steps that will help folks if they're struggling. And that dot makes it clear to me why the 5's not part of the base. What is the value of that expression in example 3?
5.
Yeah, that x to the 0 is 1. But then we have 5 times 1, which is 5. Those parentheses made a lot of difference in number 2. In number 3, with parentheses, it was 1. But without parentheses, that's 5. Number 4, how can I write that 5 to the negative 2 so that it doesn't have a negative exponent?
Take the reciprocal of it.
Take the reciprocal of the base, and that does what?
Makes it positive.
Makes the exponent positive. So 5 to the negative 2 is 1 over 5 to the positive 2, better known as 1/25. Number 5, what's the base of the exponent negative 2? Just the x. The 5's not part of the base. The 5 doesn't have a negative exponent. As a matter of fact, the 5 does have an exponent. What is it? If no exponent is written, it's understood to be 1. And if I'm having any trouble training myself to see that correctly, I'm going to write it as 5 times x to the negative 2. And then how could I write that x to the negative 2 so that it has a positive exponent?
Do the reciprocal of it.
Which makes it 1 over x squared. I don't want to leave my answer written like that because there's a simpler way to write that. As a single fraction, it would be what?
5 over x squared.
Yeah. I could put this 5 over 1 if I needed to, because that's how I multiply a whole number times a fraction. And then just multiply straight across 5 over x squared. On number 6, what's the base?
5x.
5x is in parentheses. The whole base is 5x. So what do you take the reciprocal of?
5x.
The whole 5x. What's wrong with what I just wrote? I lost my parentheses. Without those parentheses, the 5's not part of the base here. It was part of the base here. If I want to show that it's still part of the base, then I have to keep those parentheses in the denominator to say the 5's still part of the base. And then if I want to simplify it, I can say 5x times 5x is 25x squared, and I don't need the parentheses anymore. But you have to be very careful to use parentheses to indicate the base if the base is something other than just one factor. Number 7. How could I write that with a positive exponent? What's the reciprocal of -5? You said it. What is it? I gotta learn names. I'm sorry. In the middle row, tell me your name. Tell me your name. Savannah. Okay, y'all. I'm gonna have to. I don't know how I'm gonna get this, but Savannah, you gave me the right answer to a different question. If I said what's the opposite of -5, +5 is the exact right answer. What's the reciprocal of -5? 1 over -5, or we could just write it -1/5. Make sure you understand the difference between opposite and reciprocal. The reciprocal of -5 is -1/5, and that makes the exponent positive. Notice I had to have parentheses here to still indicate the negatives part of the base until I evaluate that expression. What's -1/5 times -1/5?
Positive 1 over 25.
Right. Any questions about that one? What's the difference between number 7 and number 8?
Parentheses.
The 7, the negatives was part of the base. Number 8, the negative's not part of the base. If I need to make my eyes see that clearly, I can write it as -1 times 5 to the -2. Or -1 times, how could I write that 5 to the -2 with a positive exponent?
1 over 5 to the square.
Right? 1 over 5 squared. And then what does that turn out to be? -1 over 25. So number 7, the answer was +1 over 25 because the negative was part of the base. But number 8, the negative is not part of the base, so the answer is still negative. Number 9. Only thing I can do there is rewrite it so that it doesn't have negative exponents. How would you write that with a positive exponent?
-1 over x squared.
And where's the -5? Where would it go?
Next to it, so you multiply it.
All right, so I think in your head, maybe it sounds like you just saw the dot. You said the -5 is not getting squared, just the x is getting squared. And then when you took the reciprocal of the x to make its exponent positive, then you just multiplied straight across. So that's -5 over x squared. I'm training you all to be tutors because being able to explain math helps you understand math better. You really understand it if you can explain it to somebody else. So I'm going to play like a confused math student right here. And you're going to have to tell me, calm me down. First thing you tell me is breathe. That's the first thing you tell anybody who comes in the tutor center, breathe. And then second, tell me why this is not right. I hate math because the rules are always changing. Here, the x was negative, and so you told me to put it in the denominator, but the 5 is negative, and you told me to put it in the numerator. That doesn't make any sense. What did I say incorrectly there? The x is negative, you told me to put it in the denominator. The 5 is negative, but you told me it goes up top. What should I have said? The x is not negative, it has a negative exponent. That's what you need to say. The x is not negative, we don't know what x is, that's why we're using x, because we don't know what it is. The x has a negative exponent. Did the 5 have a negative exponent? What was the exponent of the negative 5? 1. Which is why I typed this note right below those examples. The sign of a number has nothing to do with the sign of its exponent. You only take the reciprocal of something that has a negative exponent, not just because you have a negative number. The x had a negative exponent, so it ended up in the denominator. The negative 5 had a positive exponent. That's why it's still in the numerator. So if you understand that, you should be able to handle big ugly number 10 here. If I tell you that all I want to do is write that as a single fraction with no negative exponents, tell me what should go in the numerator, the top.
Negative 12y to the 5th power.
The negative 12 has an exponent. It's 1, and it's positive. So the negative 12 and the y both stayed in the numerator because they both had positive exponents. What does that mean should be in the denominator?
X cubed and z.
X cubed z. And you could put z to the first, you just don't have to write the exponent 1. All right, so on every exponent problem, I hope you're paying attention to the base. What you're taking the reciprocal of, what you're not taking the reciprocal of, what you're squaring, what you're not squaring. You have to pay attention to the base, and then we can talk about the properties of the exponents. And again, my goal is to make this make sense. 2 of the most missed problems in math are these 2. And I know one of them's x to the 5th, and I know one of them's x to the 6th, but I just got a bunch of crap floating around in my head, none of it makes sense. I'm gonna flip a coin and just pick one, all right? Because I don't understand, I just got it memorized. That is not the way to learn math. The way to learn math is to understand what this notation means, and then you don't have to memorize rules that don't make sense to you. If you just gave me 7 cubed times 7 squared, and I don't have any rule memorized, I just have to figure it out. I know 7 cubed means 7 times 7 times 7, and I know 7 squared means 7 times 7. So how could I write 7 times 7 times 7 times 7 times 7 using an exponent? That's 7 to the 5th. I have 5 7s, which is just happens to be what I would get if I had done what to those exponents originally. If I added them. And that's why the product rule says when you multiply 2 expressions with the same base, you add their exponents. Not because some dead guy 1,000 years ago made it up, but somebody noticed the pattern, and that pattern is a nice shortcut for us. Just add the exponents. Now, if I was making this a multiple choice test, look what I put for the 4 answers. I put 7 to the 5th, which is the right answer, but I would also put 7 to the 6th for folks who couldn't keep straight when to add and when to multiply. For a third answer, I put 49 to the 5th. Do you see why somebody would pick 49 to the 5th?
Yeah.
Makes perfect sense if you're not looking at this. But if you're looking at this, you go, wait, I have 5 7s. I don't have 5 49s. That's not the right answer. And then for the folks who just like to do everything possible wrong, I put 49 to the 6th. But this is the right answer. None of those other answers make sense if you're looking at what this means. Similarly with the quotient rule, the quotient rule says when you divide two expressions, well, let's play like I don't know what the quotient rule says. And I've just got to figure it out. 3 to the 6 times 3 squared. I have no idea. If I was guessing, I might guess that it's 3 to the 3rd. Did you see where somebody get 3 to the 3rd? If they like to divide exponents? Or maybe 3 to the 4th? I don't know why you would think to subtract exponents. Maybe. Or 1 to the 3rd or 1 to the 4th. You see how somebody would get those answers? Think about what it means. 3 to the 6 means 3 multiplied by itself 6 times. 3 squared means 3 multiplied by itself just 2 times. And I know that with fractions, one legal thing to do with fractions is cancel common factors. And so what's left? 3 to the 4th, which just happens to be what I would get if I did what with those original exponents. And that's why the quotient rule says if you divide two expressions with the same base, you subtract the bottom exponent from the top exponent. And you have the same caution here that we did with the product rule. Don't divide the bases. We weren't left with 4 1s, we were left with 4 3s. So don't divide the bases. Just subtract the bottom exponent from the top exponent. All right, let's talk about these 3 power rules real quickly and then we'll run out of time. The first power rule applies to this is one of the most missed examples. If I was looking at x squared cubed on a test and I didn't understand what exponents meant, I'd have to flip a coin and either pick x to the 5th or x to the 6th. But if I think about what that means, cubing something means multiplying it times itself 3 times. So that's x squared times x squared times x squared. Or if I needed to break it down even further, I could say x times x times x times x times x times x. How many x's would that be? 6. So that's what I would get if I had done what to these original exponents? Multiply them, and that's why the power rule says when you have one power raised to another power, you multiply the exponents. A to the m times n. The second power rule says if you have a product to a power, you can just raise each factor to the power. If you have a times b to the m, you can just raise a to the m and the b to the m. That next example is 5 times x cubed, and then that whole thing squared. I can just square the 5 and square the x cubed. What would that be in its simplest form? X to the what? Yep. Here's another confused math student in the tutor center. You told me to multiply the 2 times the 3, Why didn't I do the same thing with the 5? The 2 times the 5 is the 10. Why isn't that 10? I told you multiply exponents by other exponents. Never an exponent times a coefficient. The exponent of that 5 was 1, and I multiplied the 2 times the 1, just like I multiplied 2 times the 3. You can help folks understand the rules aren't changing. That takes a whole lot of the fear and the frustration of math out. All right, last one we have time to do. If I give you a fraction like 2/3 to the 4th power, if you enter that on your calculator, it's going to give you a mile-long decimal. I don't want a mile-long decimal, and I don't want you to round, because that's not an exact answer. If you have a fraction to a power, you can raise the numerator to the power and the denominator to the power faster than you can punch it on the calculator. That's 16/81. That's the exact answer. That's the answer I want you to give me, rather than some long decimal you got on the calculator. So that third power rule says if you have a fraction to a power, you can raise both the numerator to the power and the denominator to the power. All right. This happens every semester. Happened every semester for 28 years. I spend so long on the easy problems that I run out of time before I get to the big scary ones. But if you understand the easy ones, you can apply that to the big scary ones. Let me mention this to-do list at the bottom of the page and then show you one thing in momentum, and then I'll quit, I promise. This is what you need to do tonight. Read everything I gave you. Make sure you understand the policies of the course. Highlight what's important. Then register for my math lab using those instructions that I gave you and the course code, course ID that I gave you. Assignment 0 is just some questions from the syllabus and the calendar, and then a few questions that tell you how to enter answers in my math lab. Here's how you type fractions. Here's how you type radicals. Assignment 1 is your exponent homework. And then print tomorrow's notes. All 3 of those together are together in momentum. Print those notes for tomorrow. I would probably print a whole test worth at a time. I'd go ahead and print everything for test 1 tonight, and then I won't have to worry about it until I get to test 2. Printing is free in the labs, so if you don't want to use a bunch of ink on your home computer, just print at the lab before you go home. Organize your notebook, look at the calendar, play around with momentum in my math lab. You can't tear them up. Click anything you want to. You can't tear them up. Best case scenario, you'll just discover some cool tools that are there. Because I always run out of time before I get to those last 3 problems, I put those last 3 problems, go away, in YouTube. If you go to our Momentum homepage, I need this to go away. If you go to our Momentum homepage and click the YouTube link, the very first video is just 12 minutes. That's those harder exponent problems that are at the bottom of the notes. If you don't need them, don't watch them. But if you need them, they're right there. All right, everybody knows what you need to do by Wednesday. See ya. Have a great rest of the first day of the classes.